Okay, -1. Okay, today we're finishing up 12.5, which means we're gonna do all of the planes and stuff. So where does that bring us? Second half of 12.5, but also I think we missed one page from the last set, so I'll start with just a quick overview of what that looks like. To hopefully catch us up to what's on today, because I think today will take just as long as last week did. So we closed last week by just barely defining distance from a point to a line. We said we wanted to find that distance by projecting a vector onto something else. In particular, we'll take the orthogonal projection to this one. Since we have a line, we know its direction vector. And the orthogonal component to that direction vector is going to be the shortest distance between a point and a line. All right, we want to take that perpendicular shot straight to get up to the point. Or maybe from the point straight perpendicular to get to the line. I have, of course, heard it both ways. But that means we could pick any point that is on the line. Doesn't matter what point it is at all. All I need to do is just project its component onto that orthogonal element. And for any point I pick, that orthogonal projection is going to end up being the same. So point on the line doesn't matter. I only need to know about the point I'm going to. But since I'm looking for an orthogonal projection, I'm going to want some kind of a cross product. Since a cross product can always get me a vector that's perpendicular to the thing that I was working with. So we'll use, again, cross product to help us figure out that orthogonal bit. But really, it comes from the idea of taking that magnitude of that vector, that hypotenuse, and looking for that hypotenuse multiplied by the sine of theta. And we were able to build that into a magnitude of a cross product. So a worked out example, I've done it a couple of ways, which I won't go over too much now because I've got the work just you can take a look at later. But effectively, I found my two vectors. The direction vector is easy. It's just given to me in the equation, or nope, take that back. It's still easy though. But I'm finding a line that contains 2 points. So find the distance between them to get the vector or the vector between them. So get my direction vector for the line. Pick any point that is on that line. I happen to choose 1, 1, 0. Found the vector that connected it to 0, 1, 0, took a cross product of those two things, and then did a couple of magnitudes, one divided by the other. Cool. So that is that whole thing. Sorry if you were writing some of that down. Pause for just a second. If at any point in time you want to go back and look at any of the notes that I've covered in class, I have them available on D2L. You can find them as soon as I write them down because they update live. So if you just go to our lecture, or I guess my lecture, the one that's got my name on it, it's in the folder in D2L, in the content folder in D2L. There's a link to this document. Everything I do in class is under the tab called live streams. You can see it over there on the left part of the screen. And then if you just want a completed version of all of the notes, you can look in the purple section, but I'm also building that as we go this year. So, but yeah, the purple section, Fall 25 notes, basically has the same thing, just maybe those notes are a little cleaner than what I write in class. All right. And we got that part done in like less than 5 minutes, so good for us. So the other half of 12.5. First we did lines, now we're going to do planes. Planes kind of being the 3D equivalent of a line. Step this thing up. A line is still going to be a completely linear function, just like a line is linear. Planes also have that same thing. Each of x and y and z to the first power, making it, again, a linear equation. And probably even a linear function, as long as the thing doesn't bend back around on itself. But the way we're going to create the equation of our line. If I think about this plane, said equation of a line, but I meant an equation of a plane. I think about a plane in terms of the vectors that are contained within it. Let's see this blue diagram drawn over here on the right side of the screen. If I think about all of the vectors that are contained in that plane, let me try that again. If I think about all of the vectors that are contained in that plane, they share one element in particular that's in common between all of those vectors, in that they are all going to be perpendicular to that red normal vector that I've drawn in. More on why we're going to call it a normal vector in a minute, probably. But each of the vectors, each of those blue vectors that are inside that plane, all are going to be perpendicular to the red vector that I've drawn in. Doesn't matter where I draw them in the plane, that red vector, which comes straight out of the plane, is going to be perpendicular to all of them. So if I wanted to be able to write an equation, talk about the plane, it might be easier to just write an equation that talks about every possible vector that is inside this plane, every possible blue vector. And I know that if two vectors are perpendicular to each other, their dot product is going to be 0. And so that's where I'm going to start my equation for a plane. Right up here, this top line, taking some vector n, which again, we're going to call it the normal vector. It's going to be perpendicular to the plane. And if I take the dot product of any vector that is in that plane with n, I should get 0. So how do I write a vector that is in the plane? Well, I want to use just regular old r, the vector value r, to be x, y, and z. So if I start just drawing on some of this stuff here, hey, come on, don't be like that. There we go. So r, I'm going to use as the vector of x, y, and z. So those are all variables. P0 is just going to be some point in the plane, just like the last example where we were looking at distance from a line to a point. I needed just any point on the line, didn't matter which one. Same thing here, any point that's on the plane will not matter which one. I just need to pick one. And say if I take the difference between my variable vector, x, y, z, with the point, x naught, y naught, z naught, subtract those two, I want to get a vector then that lies completely within the plane. And then take the dot product with n. As long as it's 0, then r is a vector that ends up in the plane, or at least r ends up being a point that is in the plane, the direction vector for a point in the plane. And we're going to simplify that equation a bit to give us maybe a more scalar version of what that plane equation can look like. We can write it out as a vector or as a vector valued equation, but if it's a dot product, I know the result of that thing is going to be a scalar. So I should be able to write out a scalar valued function that gets me there in the end. So one of the more common ones is the one that we see right here. That's a times x minus x naught, b times y minus y naught, plus c times z minus z naught is equal to 0. And that should hopefully remind us at least a bit of point slope form back when we had just equations of lines. Right, we had some slope times x minus x naught is equal to y times y minus y naught. Very similar things going on here, but now there's a term for each x, y, and z. And we can get that equation just by working out the dot product listed above. I tried to track the normal vector in red through the whole problem. So it's going to be that ABC that we keep seeing show up. But if I want to simplify the whole thing, the easiest way to write down the equation of a plane just be ax plus by plus cz equals d, where d is just some constant value related to the point that is in the plane, and I just moved all of those numbers over to one side of the equal sign. The nice thing about this standard form for a plane equation is that it has the normal vector baked into it. I can just grab the normal vector by collecting the coefficients on x, y, and z. Put all of that together. And just a quick example, if I want the equation of a plane orthogonal to a vector 1, 4, -2, and goes through some point, I can just plug that into what is kind of like the point slope equation for a plane. Maybe that one's, or maybe this one is standard form and the other one's general form. The particular words aren't going to matter too much to us, but I can just plug those bits in and then either leave it in just its original form where I've got a normal vector and a point plugged directly in. It's a totally valid version or a totally valid equation for a plane. But if you'd prefer to simplify it, I got the equation there at the bottom. X plus 4y minus 2z equals -14. To again just hit some highlights, if I want to find the point of intersection between a line and a plane, I can just plug the equations of the line into the planes. All right, so my line has an x, a y, and a z component. I plug those in for x, y, and z, solve the thing for t, and then plug it back in to find my point. And finally, if I'm looking for an equation of a plane from the minimum number of components, I know that 3 points. 3 points defines a plane. So any 2 lines. Let me just try that once more from the top. Back in algebra, we knew if we had any 2 points, we could just connect them to find the line that contains those 2 points. 2 points was always enough to define a line. If we're going to step up to another dimension, it's going to be any 3 points can define a plane, as long as those 3 points aren't all on one line. So the minimum number of constituent pieces I need to construct a plane is just 3 points. So if I have 3 points and I want to find the plane that contains them, I'll just find a pair of vectors connecting between these 2 points. I chose QP and QR, you can see in the diagram. And because those 2 vectors, QP and QR, must be in the plane, since they connect points that are in the plane, their cross product will end up being perpendicular to the plane. So since I'm usually looking for a normal vector when I'm trying to make a plane, so just any vector that's perpendicular to the entire plane, that's what I'll want to sort of define the thing. The easiest way to find that normal vector, if I've got to build things up from the base principles, is to just take a cross product of any 2 vectors that are in the plane. So took that cross product, came up with an equation, and I got x plus y equals 1. And one point I want to highlight on here is that I constructed this plane using 2 slightly different normal vectors. Because I originally did my cross product and I got 3, 3, 0. But really, that's just 3 times the vector 1, 1, 0. So, right, so I can factor a 3 out of that normal vector. And using either normal vector, I can get the same equation for this plane. Meaning that the normal vector to a plane is not unique, just the direction of that normal vector. Unique. So using either 3, 3, 0 or 1, 1, 0, I can come up with an equation for that plane, which means if you want to simplify your work a little bit, or just make some of the math that you do, some of the arithmetic that you do a little easier, you can simplify down your normal vectors. All right, on to the fun part. Stuff where we'll actually work through some examples instead of just me talking about them already being done. So, if 2 planes are going to intersect, the little picture over there. If 2 planes intersect, they are going to intersect along a line. Doesn't matter what orientation I use for those planes. long as they're not parallel to each other, they're going to intersect, and their intersection is going to create a line. If these two things are intersecting at some line, I ought to be able to find an angle of intersection that's between them. And we're going to use the idea of the dot product to figure out that angle. In particular, I know that the dot product of two vectors is pretty closely related to the cosine of the angle that's between them. That's from our geometric definition of the dot product. And you can sort of see it solved for theta there on the right half of the screen. Just like lines, we're always going to be looking for the acute angle that forms when two planes intersect. So very similar to two lines intersecting, there's always going to be a pair of acute angles and a pair of obtuse angles. They're right across from each other. I believe vertical angles is the technical definition. But because we're just going to standardize the idea, we're always going to look for the acute angle of intersection between two planes. Even though if I look for the angle between two vectors, that value could be obtuse. To fix that, we're just always going to take the absolute value of the dot product when we're looking for angles between planes. So very similar to last week, looking at angles between lines. We're looking for angles between planes. Same thing. We want the absolute value of the dot product to ensure we get an acute angle, or possibly 90 degrees. But yeah, fun part about all this is that two lines are going to have the same angle of intersection as the angle between their normal vectors. And that's really what's going on with this picture over here. The angle between those two normal vectors, n1 and n2, is the same as the angle between the planes. So let's figure some of that stuff out. So first, if two planes are going to be parallel, then they're going to end up having the same normal vectors. So if I were to look at the normal vectors for the two planes on screen, let's see, this guy looks like 1, 1, -2. And for the other normal vector, that looks like -2, -2, 4. Maybe I should be emphasizing where I got that stuff from. I want to put all of my terms on one side in order to have this plane in its general form. So if I just gather all of those pieces on one side, I think those are the numbers I get. And then it looks to me like n2 is just equal to -2 times n1. If I just compare those two normal vectors, so they are parallel. Parallel. Right, in order for two vectors to be parallel, I just need one to be a scalar multiple of the other. And that's what we have right here. And again, two planes are going to be parallel if their normal vectors are parallel. So almost every time we want to talk about the direction or some kind of a direction for a plane, we're going to be referring back to its normal vector because that's going to be the easiest way to sort of describe what's happening with that shape somewhere out in 3 space. Figure out where its normal vector is pointing. Right. Then if we're going to figure out a line of intersection between a couple of planes, well, let's take this to the definition of a line, which is R of t is equal to R naught plus TV. Right, so if I needed to come up with the equation of a plane, or no, try that again. If I needed to come up with the equation of a line, I just need any point that is on that line. And I need a direction vector or a parallel vector for the line. So I'm going to try to come up with those two things. First off, if I want a point that is on the line, and this line is the intersection between two planes, I am looking for a point that is on both of these planes. Right, so if I just come up here and look at this line of intersection right here, and maybe it's got some direction going that way. Right, that's the line I'm going to be looking for. Any point that's on that purple line will do. Which means that, again, it just needs to be on both of the two planes. In terms of the math equations that I have, that means I need to find a point that satisfies both of those two equations. And I have a free variable again, or a free choice variable. Right, I have two equations with three unknowns, which is an overdetermined system. I can at most solve for two of those variables, which means I just get to pick some option for the third variable. Since there are an infinite collection of points that make up this line, I get to just choose one point. So there's going to be one point on here where, say, z is equal to 1. And once I know that z is 1, I can then figure out x and y. But I get to choose anything I want, kind of, when I make this first choice. And we'll see in a minute that there are going to be some restrictions sometimes, and I think this is one of those cases, but I'll talk about that once we're done. So again, I chose z equal to 1, I don't know, for no particular reason. I guess if I look at the first equation, x plus y plus z equals 1. If I choose z equal to 1, I can then just say that x is equal to negative y. Right? I can get rid of the constant term out of the equation on the left if I let z equal 1, or if I let y equal 1, or if I let x equal 1. Any of those just simplified the equation on the left rather nicely. So I decided to go with that. So if I let z equal 1, that means x plus y equals 0, and x plus 2y is equal to negative 1. Right, if I just plug in 1 for z, those are the two equations I get. So from here, I don't know, how about I solve this thing for x first? X is equal to negative y. Substitute that into the other side. So negative y plus 2y equals negative 1, which means y is negative 1. Bring that back around. If y is negative 1, that means x is positive 1. I'm just kind of draw in some arrows to kind of explain my thought process there for solving that system. So I end up with a point, and that point is 1, negative 1, 1. So that point lies in both planes, which means it must be on the line of intersection. I could check it real quick by plugging that point back into the two equations above. 1 minus 1 plus 1 is 1, and then 1 minus 2 plus 2 is also 1. So we've got our point. That's the R naught part figured out. For the next part, I need to come up with a direction vector for the line. So I need to be parallel to that purple line right there, something that tells me what V is. And if I'm looking at the way this thing is constructed, V needs to lie in both planes, which means that V needs to be perpendicular to both of those normal vectors. Right? If V is in the first plane, it's got to be perpendicular to N1. And if B is in the second plane, it's got to be perpendicular to N2, which means a pretty easy way to find V would be to just take the cross product of those two normal vectors. So that's what I'll do down here. V, my normal vector. It's the cross product of N1 and N2. And a cross product, if we write it out, I, J, K. Crossing with our two normal vectors, which are 1, 1, 1 and 1, 2, 2. 1, 2, 2. Put all of it together to find something. Hope that there's enough space. This looks like 2 minus 2, which is 0. Then I'll have 1 minus 2, which is negative 1. And finally, 2 minus 1 is 1. That's the cross product I get. So put that all together. R of t is 1, negative 1, 1 plus t times 0, negative 1, 1. So that, I think, is the equation of my line. So I said at the beginning that we got a free choice of just v equals 1. That is mostly true. I do get to make one free choice at the beginning, but because of the direction vector I ended up with, there are some bad choices here. In particular, I can see from my direction vector that there is no change in the x value. Which means if I try to pick a point where x is anything other than 1, it's not going to be on the line of intersection. Because this thing ends up running parallel to the x-axis. So since that variable doesn't change, in my free choice, I just need to pick y or z equal to anything that I want to. Because x has to be 1 no matter what. Hi there, question back. Would it be better to do the cross product first? Sure, probably. I suppose when I was working through this problem the first time, I did the cross product first. I usually do the cross product first when I solve these problems, actually. For the first one, it just seemed easy. I wrote down R naught first, so I started talking about it first. But yeah, I generally do the cross product first. And then yeah, that way you will know if one of those entries is 0. That means that variable won't be changing. So in this case, we can see x always has to be 1 in order to get this equation to work. But yeah, right. So if we're looking for two non-parallel planes, their line of intersection is the direction vector of the cross product of those two things. So coming to an angle of intersection between two planes. Again, we'll be getting it from the geometric definition of the cross product, which means I need a pair of normal vectors. So it looks like those normal vectors are going to be 3, 6, negative 2. And 2, negative 1, negative 2. Right, if I just collect, nope, 2, positive 1, negative 2. I moved it over in my head and then gave it another negative sign. So maybe I should just not do it over in my head and actually write out what I did here. 2x plus y minus 2z equals 5. Right, just rewrite that plane equation so that all of the variables are collected on one side. And what do we want here? Probably a magnitude of each of these two things. Should it be -6? It should. Once again, I heard a bunch of whispering. I'm like, there's a mistake on there somewhere. As soon as the whispering grows loud enough, I'm like, yeah, you guys are probably right. Yes, 3, -6, -2. Somehow managed to drop the negative that was really easy to see and then add an extra one where there shouldn't have been one. Oh well. But yeah, so I wanted also to get the magnitude of these two normal vectors, which looks like 9 plus 36 plus 4, and a magnitude of that second one, 4 plus 1 plus 4. So the square root of 9 is 3. And on that first one, 36 and 4 is 40, plus 9 is 49. Square root of 49 is 7. Not as much whispering that time, so I think those numbers are right. So how about a dot product of those two? N1 dotted with N2 is going to be 6 minus 6 plus 4. I believe that's 4. Cool. So then to get that angle, I want the cosine inverse of the absolute value of 4, which I'm just going to emphasize, divided by 7 times 3. And that comes out to a number. Hopefully someone's got a calculator out there. That's pretty close to a 90-degree angle, so I bet this is like 1.5-ish radians. Maybe 1.50. I would only be guessing if I put a third number on there, so 5? What you got? 1.379. Not that close at all. 1.379. Anybody else get that same number? Excellent. 1.379. Cool. All right, and one last concept. I think we might actually finish the notes in time today. Can you believe it? So we started, well, we sort of finished last week, but really started today, with finding the distance between a point and a line. So now we're going to find the distance between a point and a plane. To sort of keep these two ideas somewhat similar. And again, we're going to get there by looking at a projection of some kind. So I am going to collect any point I want, some point I'm looking for that's out in space. Presumably that point is not going to be on the plane. The point we're on the plane, the distance to the plane would be 0. That's somewhat of a boring result, so we'll ignore that case and instead look for some point that is not on the plane and figure out the distance to that plane. Again, I think the shortest distance between a point and a plane is just the straight line distance that gets me directly to the plane, which means I am going to be looking for the spot where, or the line that connects P to the plane that will intersect the plane perpendicularly, or an orthogonal intersection to that plane. All right, if I take any other line that is not that orthogonal line of intersection, I'm going to have a longer distance than just going straight at the plane. So, if I'm looking for that orthogonal intersection line, orthogonal line of intersection between the point and the plane, that line is going to be parallel to the normal vector. But finding the point of intersection between that orthogonal line of intersection and the point that's out in space, I'd need to find the line first if I wanted to figure out that point. So finding it's going to be rather hard, but I could take any point that is on the plane, not necessarily the one that's closest to the point or close. Yeah, I don't need the point on the plane that is closest to my point in question. I can take any point that is on that plane, construct that purple vector, and then just project it onto the normal vector. Right, so I'll find, again, the distance between my point and anywhere on the plane, and then just project that thing onto the normal vector. That should give me my shortest straight line distance between these two objects. Which means we're just coming back to a projection. Really, I need the magnitude of the projection, which is just going to be the component of my vector that's in the direction of the normal vector. But because I just want to consider the distance as a value, I'm not really defining a positive and a negative side of the plane. I'm going to take an absolute value of that component, so that my distance is a positive number. Again, we don't really want to define a forward and a backward side of the plane, at least not yet. So distance will be an absolute value. I don't care if I'm on the right or the left side. I just want to know how far away I am. So it's got a very nice looking formula, just the dot product of my vector v with the normal vector divided by the magnitude of the normal vector, because I don't care how long the normal vector is. The only magnitude I care about is the one that connects my point to anything that's on the plane. So I really just needed the unit normal vector. Normal vector's direction shouldn't matter to us, which means if I want that distance to construct it in terms of some point P and a plane containing R with a normal vector N, it's just the dot product of RP and N divided by the magnitude of N. And if you like, that equation can simplify, kind of. So I think that the equation for distance we already have is fairly simple, or at least it's kind of easy to remember. It's only got two elements in it, whereas the expanded out formula is a bit of a bear, but it can work. And over to the right, I've sketched out how I think that works. And I'm going to go quick because I want to actually hit some more examples of this stuff. But say I've got, the equation of some plane and a point out in space that I want to be connected to. I'm going to claim that the distance is this absolute value divided by the square root of a squared plus b squared plus c squared, which is really just the magnitude of the normal vector. And to highlight the fun part of where that equation comes from, let's talk about what's right here. I need a vector that connects 2 points, P0 and P1. That's what I've decided to call them. P1 is my point in question. That's the one where I want to find the distance out to that point. But P0 just needs to be any point that is in the plane. But I don't necessarily know what that point is going to be. I have to go pick one. But I'm going to argue that it doesn't actually matter what point I pick in that plane, because if I take the dot product of its position vector with the normal vector, that's exactly what I've got going on in the equation of a plane. So if you look at the parts that are highlighted in blue, in particular ax naught plus by naught plus cz naught, that is just the normal vector of my plane dotted with the position vector to a point that's in that plane. And the equation of the plane tells me what that's equal to. In particular, it's equal to that number that's on the other side of the equal sign. So for any blue point, ax naught plus by naught plus cz naught is equal to d. Or in this case, it's negative d because of the way that the textbook wrote the equation. So this sort of simplified version of the distance equation for a plane does have a caveat that we have to make sure that we pay attention to, because it was defined as this equation right here. It is put in what actually is general form, where we put all of our terms on one side and set it equal to 0. So we've shifted the constant term over to the left first. It means if you want to use the sort of expanded version of the distance formula for a plane, make sure your constant term is moved over to the left side with everything else. Cool. Okay, and then I said I wanted to do that kind of quick because I do still have a few more examples to get to. Hopefully we still get that. All right, the distance between my point 1, negative 2, 4 and the plane 3x plus 2y plus 6z equals 5. Well, I need to pick some point. So we go with find r. Or maybe let's go with notice r. I don't know. I need to pick a point that's on here. I have 2 free choices now. The first point that jumps out at me is 1, 1, 0. It's on the plane. Is on the plane. So how did I get that? Because I did just kind of pull that number out of my somewhere. It's equal to 5 over on the other side. I have a couple of free choices. I said, all right, let's just let z be equal to 0. Because 6 doesn't divide nicely into 5. I don't really want to deal with it. So cool, z equals 0, it's gone. Then I've got 3x plus 2y equals 5. And I notice rather conveniently 3 plus 2 is equal to 5. So x and y can be 1 and 1. It solves the point. There's more art than science to figuring out points that are in these planes. I'm mostly just kind of making stuff up and finding that it works in the end. That's really the best way to find these points. There is a slightly more systematic way, but it still involves just, I don't know, I feel like 0 is a good value for z. And then you just do that and something nice comes out. Could have also chosen 0 for both y and z, but that means that x then needs to be 5/3. Didn't really feel like dealing with a fraction. So I chose 1 and 1. Again, more art than science. But now that I have that point, I can just figure out what RP is. RP is the vector 0, negative 3, 4. All right, if I subtract 1, 1, 0 from 1, negative 2, 4, I get 0, negative 3, 4. And I see my normal vector already. It is 3, 2, 6. So my distance then should be the dot product of those two. RP dotted with n, take its absolute value, and divide by the magnitude of n, which is 0 minus 6 plus 24 divided by the square root of, is that going to be square root 49 again? 9 plus 4 plus 36. Yeah. Again, I still wanted the absolute value up here, but that's just going to work out to positive 18 divided by 7. You could also use that other equation that we were going with. But again, if you're going to use, excuse me, if you're going to use this formula for distance, just make sure that you gather your constant term on the left side. Right? At least with the way that it's written out in the textbook, it had that constant term gathered on the left. So make sure you do that as well. I'll leave the rest of that as an exercise though, not skip over that too fast. Maybe just enough to bring both examples on screen at once. Okay, so let's consider a line and a plane. And I want to do a couple of things. If they intersect, find the point of intersection. If they don't intersect, find the distance between them. I'm considering there is an example where we already found the point of intersection between a line and a plane. I'm gonna guess this one does not do that. Well, let's justify why. So I would probably pick out my direction vector for the line. It looks like it's 4, 2, -1, blah, blah, blah. 4, -2, -1. No, 4, +2, -1. Where am I getting all of these extra negatives today? I have no idea, brain. Yeah, 4, 2, -1. I'm pulling that out of the line, so it's just the coefficients on t. I'll also want the normal vector for the plane, and it's just 1, -1, 2. Anytime I'm looking for whether or not things intersect, if I'm looking for directions of lines and or planes, then grabbing their direction vectors and normal vectors is probably a good way to start that. So how am I going to check to see if these things are parallel? Well, I know that if a line is going to run parallel to a plane, then, well, let me start with a secondary example first. If a line is parallel to the normal vector for a plane, then that line is going to be orthogonal to the plane itself. Just like normal vector, some line that's parallel to the normal vector, that's going to go straight through the plane. It's going to intersect it orthogonal. I don't know if that visual is helping out at all. So I don't want these two vectors to be parallel to each other. Instead, if I want a line and a plane to be parallel, I want the direction vector and the normal vector to be perpendicular to each other. I want those two things to be orthogonal. If the normal vector to a plane is also perpendicular to a line, then those two things are going to come out parallel. The plane and the line will be parallel, but not the plane, or not the line and the normal vector. So I want these two things to be perpendicular if I end up with a plane, or if I end up with parallel objects. So I should take their dot product. I should also apparently just kind of hang it up and quit talking today. This doesn't seem like any of the words are coming out the way I want them to. But if I take that dot product, I get 4, -2, and then -2 again, which is 0. So that 0 means that these things are parallel. Parallel. So since they don't intersect, I want to find the distance that's between them, which means I can use the distance formula that we already have. 2z minus 5 equals 0. So I'm just going to bring that -5 over. I just need the distance between any point that is on the plane and or any point that's on the plane and any point that's on the line. I know they run parallel to each other, so it shouldn't matter which one I pick. So I'll just grab any old point. Might as well go with 7, 0, 1. because it's just given to me in the equation of the line. And then I can plug that into the distance formula, which will look like 1 times 7 plus, or no, minus 1 times 0 plus 2 times 1 plus -5 all over the square root of 1 plus 1 plus 4. And then whatever that resolves out to is my distance. All right. Almost got through everything today. Just one last example short. So since I missed it, I'll update it later. But also, if you go look at the notes section in the top, you can find some of these problems already worked out. Ooh, that's not good. Don't do that. Cool. There it is. Anyway, yeah, we'll stop here. I will see you guys again on Wednesday. Okay, bye, 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 bye. Thanks. You as well. All right, and